Okay, it is now time for us to kind of reap some of the fruits of all this stuff we've been working on. We're going to kind of pull it all together here and show you how we can use the sum notation and rules and formulas in order to find the limits of Riemann sums, which will give us the exact area underneath a curve. So let me first kind of explain what's going on, and then we'll do a couple examples. So let's say you have some function, y equals f of x, and you want to find the area, let's say, between a and b. And so what you do is, we can estimate it by splitting this up into a number of rectangles. And then what I'm going to do is I'm going to choose the right endpoint of each of these intervals. Of course, you could choose the left endpoint, the midpoint. You could actually choose any number in the interval. And so when the book actually defines the Riemann sums, it does it very generally. So it gives you a lot of freedom, and there's a reason for that, because if you're wanting to use the definition on a function that isn't continuous, but it only has a finite number of discontinuities, you can break up your partitions at each of those continuities and just deal with them like that. And so we're going to just always be using this. We're going to assume that we have this nice continuous function, and then we're going to just assume that these intervals are equal width, equal length. Okay, and so the width of one of those intervals, then we're going to call the width of the interval delta x, and the width of one of those intervals is going to be b minus a divided by n. And this is where n is the number of rectangles. Okay, and so you got n rectangles, and so we could say then that the area underneath this curve is approximately equal to the sum, and this is we'll say k equals 1 to n. So you're going to add up all these different rectangles, and then this is the ck is going to be either the left endpoint, the right endpoint, the midpoint, and technically it could be any other point in the interval here underneath that rectangle. And then you're going to have like this delta x. Right? And so this is going to give you the area of one of those rectangles, and you're going to sum up all n of those rectangles. Okay? And that's the idea, but we need to break this down a little more. In particular, we need an expression for this point that we're going to use, the ck. We need some expression involving k and n and stuff. The delta x, like I said, we're going to use this expression for our delta x. And this expression is basically saying that you're dividing a to b into n equal intervals. Okay? So now what I'm going to do is I'm going to write the endpoints of these intervals down. We'll kind of write them as a set. So you have like the point A is the left point, and then the next one would be, you would have like a plus delta x, the width of the interval, right? And that would give you this next endpoint here. And then for the next one, you would do a plus 2 times delta x. And for the next one, you would do a plus 3 times delta x. So you're getting that endpoint, that endpoint, that endpoint. And you would keep going, and then you would get a plus somewhere, if I stop here in the middle, however many there are, you'd have k times delta x. And then you'd keep going, and you would get like a plus, and then you would have n minus 1 times delta x, and then you would have just b. And b would be like n times delta x. You have 1, 2, 3, 4, 5, 6, 7. So this is splitting this up into 7 rectangles, right? And so a plus 7 times delta x would give you the b. So these are like these endpoints here. And so what I'm going to do is I'm going to choose my c, where I'm evaluating the height of the rectangle at each point. I'm going to choose it to be the right endpoint. Okay, and there's a reason I'm going to choose it to be the right endpoint and not, like, let's say the left endpoint. And the reason for that is that I'm going to want the expression here. So let me write CK. My CK, in terms of the kth rectangle, like the first rectangle, the second rectangle, the third rectangle, I'm going to let this expression be a plus k times delta x, if that makes sense. Okay? And so when k is 1, I'm dealing with the area of the first rectangle. And so when k is 1, here, I'd be plugging 1 here, and I'd have a plus delta x, which gives me the right endpoint of that rectangle, of the first rectangle. So when you have k2, you're dealing with the area of the second rectangle, and so you plug 2 into here, you would get a plus 2 delta x, and then you're getting the right endpoint of the second rectangle, and of the third rectangle, and so on. Okay? So that's going to make things a lot simpler, because if I wanted the left endpoint, then this would have to be k minus 1. Does that make sense? And then you would have a more complicated expression. So this is what's going to, using the right endpoint is just going to simplify the expression, simplify the algebra. So that's what we're going to use. And so plugging it into this, my Riemann sum here would be like the area is approximately equal to the sum as k equals 1 to n of f of, and then I would have a plus k times delta x. So this is just plugging in the ck, okay, which is this here. And then I'm going to multiply this by the delta x. Okay, and that is my Riemann sum. And then I'm going to be able to simplify this down using the rules and the formulas that we learned earlier, and then I'm going to be able to take the limit of that. Okay, well, for some functions we'll be able to take the limit of that. Okay, now that looks pretty simple, but we still have to plug it in. The delta x is still this, b minus a over n. So this would actually be equal to the sum as k equals 1 to n of f of a plus k, and then my delta x is b minus a over n. So maybe I'll do a nice square bracket here. And then this delta x is again b minus a over n. And now that is my official Riemann sum. So this is you can say here that this is a Riemann sum with n equal with intervals or rectangles using the right endpoint to get the height. Okay, and so basically you would have to plug this expression inside whatever your function is and simplify all that, simplify it with this, and get it down, if you can get it down into where's my, if you can get it down into an expression involving one of these four formulas, then we're going to be able to express everything in terms of n, and then we're going to be able to take the limit. Okay, so like I said, this is complicated, but it makes sense. I think it really does make sense, and it feels good when you plow through it and you actually get the right area. You really have a sense of accomplishment. So this is one of the things when I learned how to do, it's like, oh wow, this is cool, this is neat. And so I hope you feel the same way. So let's go at it. And notice that what's interesting is k only comes in this whole formula. It only comes in there, but of course you're placing that in the function and stuff, and then you have to simplify. So what I'm going to do is we're going to use this for that original example that I gave, and I think that what we did is we just did a nice simple function, y equals x squared, and we did it from 1 to 3. Right? And we found the area underneath the curve here from 1 to 3. Okay? So my delta x here is going to be, my a is equal to 1, and my b is equal to 3. So my delta x is going to be 3 minus 1 over n. So my delta x is just 2 over n. Okay, and what we're going to do is we're going to pick the right endpoint of each interval, and that's your ck. And so my a is 1. So remember the right endpoint was I'm sorry, the right endpoint, the formula was a plus k times delta x. Okay, so my a is 1 plus k, and my delta x is just 2 over n. Okay, so we could simplify this to 1 plus 2k over n. We'll simplify it into that. Okay, so now my Riemann sum for n rectangles, what I'm going to do is I'm going to do k equals 1 to n of f of this, like f of 1 plus 2k over n, times my delta x, which is just 2 over n. So it'd look like that. Okay, and then I can, I'm going to go down here, and I could rewrite this as k equals 1 over n, and I'm going to plug the 1 plus 2k in, 2k over n, I'm going to plug that into my function, which is x squared. So that's really going to be 1 plus 2k over n quantity squared. So that's this in the function, and then I got to multiply that by 2 over n. So what I'm going to do is I'm going to keep doing it like this until I get an expression all in terms of n. And then I'm going to say that my area is equal to the limit as n goes to infinity, and then find the exact area. So I'm going to do that instead of saying the area is equal to the limit of this, and then I'd have to say the limit of this, the limit of this, the limit of this, and I'd have to keep writing that. And so it'll be simpler just to get my expression and then write a new statement that says the area is equal to, and then the limit of. And so notice I'm putting a lot of thought into how I express it, so what I'm writing is a true statement and is clear and things like that. And that's important, especially when things start getting more and more complicated. Okay, so now what I'm going to do here is I'm going to have to FOIL that out, right? So k equals 1 over n, and this is going to be 1 plus 2 times 1 times that, which is just 2k over n, plus this 2k over n squared. So it's like this times 2n. So it's the sum of all of this. Okay. So now I'm gonna distribute this through there. K equals 1 to n. And so distributing this through, and then I'll do some simplifying here too. So, well, actually, I'm going to go ahead and just do some simplifying first, I think. So this would be 1 plus 4kn plus, this would be 4k squared over n squared all over 2 times n. Like that. And so now I can rewrite this like this. K equals 1 to n. And then I'm going to distribute the 2n over there. So I'm going to have 2n plus 4k, I'm sorry, 8k, because I'm distributing the 2n over n squared plus 8k squared over n cubed. And so now I get all of this. So now I'm going to break up this over the sums and pull out, well, let me just break it up over the sums first. Really write the steps out to make them clear. This is 8. And so now I got these sums. Now remember, with respect to k, n is a constant. So this is like the sum of a constant, right? This here. And so so this would just be 2n times n. Okay, now for this one, I'm going to pull out 8 over n squared, and I'm going to be left with 1 over n squared. This would be n equals 1 to, I'm sorry, k equals 1 to n. And then this one I'm going to take out 8 over n cubed, and then I have the sum k equals 1 over n k squared. And you know what? I did this. I'm not sure why I wrote this here. When I pull out, and this video is good up to this point, when I pulled out the 8 over n squared, this whole thing should just be k. Okay? That should just be k. I'm not sure what I was doing. I think the phone rang and that distracted me. And we have an Amish guy coming today to check our windows. And that's probably who it is, so I think my wife got it. So that should just be a k, sorry. So now when you look at this, notice that that what you have here are the sums of these formulas. You have one of these, a sum of k and a sum of k squared. That's all that's involving the summation notation. Oops. So now what I can do here, so this here is just going to give you 2, and then this here is going to be 8 over n squared, and then I'm going to plug in, let me bring those formulas back. I'm going to plug in this formula, because that's just the sum of k. I'm going to plug in this formula here. So this would be n times n plus 1 over 2. Okay, and then this is going to be 8 over n cubed, and now this is the sum of x squared. So now I'm going to plug in that formula. Okay, so that formula is n times n plus 1 times 2n plus 1 all over 6. And so then I got this whole expression, and then I got to simplify this and take the limit as n goes to infinity of that. So let me keep simplifying here on my next page. So let me write that last one out. What I'm going to do is I'm going to go ahead and I'll just write an 8 here and an 8 there, and then put the n squared there and the n cubed there. So in other words, I'll do a little simplifying on this expression, and what I get is 2 plus 8n plus 1 over 2n squared plus 8 times n plus 1 times 2n plus 1 over 6n cubed. Okay, now this time I'm going to go ahead and simplify this all out, but then I'm going to show you what I would normally do, kind of a shortcut here. But first I want you to see by actually simplifying this out. So this would be 2, and then I could cancel this out, that'd be a 4, right? So then I'm going to distribute the 4n over, so this would be 4n squared plus 4n all over n squared, and then this would be plus, and then this would be a 4 and a 3, so this would be 4n, I'm going to keep it like this for now, 2n plus 1 all over 3n cubed. So I got all of this. So now what I'm going to do, I'll rewrite this. And now I'm going to FOIL that there. And so this would be 2n squared plus 3n plus 1 all over 3n cubed. And now I'm going to rewrite this, 2 plus, and we got this again. And now I'm going to distribute, this is my final step, that 4n over. So then that would be 8n cubed plus 12n plus 4n all over 3n cubed. And so this is my simplified expression. So the actual area that I'm looking for is equal to the limit as n goes to infinity of this whole thing, right? 2 plus 4n squared plus 4n over n squared plus 8n cubed plus 12n plus 4, and this should be 12n squared actually, plus 4n all over 3n cubed. So it's equal to that limit. Now, okay, now what I can do is break the limit up over the sum, and I'm not going to write that out. This is just 2. Okay, now when I take the limit as n goes to infinity, this is a rational function where the degree of the top is equal to the degree of the bottom, and the limit as n goes to infinity is the horizontal asymptote. As you go out to infinity, the graph is approaching that horizontal asymptote, and when the degree of the top is equal to the degree of the bottom, then the horizontal asymptote is the ratio of the leading coefficients. So for this, I just get 4 over 1, or just 4. And then this one, the ratio, again, n cubed, this is the ratio of the leading coefficients. So I get 8 cubed. Okay, so then this would be 6 plus 8 cubed And so this would equal 18 cubed plus 8 cubed, which is 26 cubed, and that as a decimal is equal to 8.6 repeating. And that, if you go back and look at the very first video where we found the area between 1 and 3 under x squared using the Riemann sums, the exact answer was 8.6, or 8 2/3. And so this actually gives me the exact answer, okay? But there was a lot of work there. A lot of work was involved, right? But let me show you one quick shortcut. That when you're at this point, I could have jumped straight to like this down here very, very quickly. And the reason is I know here that these are going to be a polynomial on top and polynomial on bottom, and I can tell that the top is a second degree and the bottom is a second degree. And so really I just need the ratio of the leading coefficients, which is going to be 8 and 2. Right? 8 halves, which is where I got before, right here. And then here, again, this is going to be a third degree, this is a third degree. So I just need the ratio of the leading coefficients here, which is 8 over, but I have to be careful. It's not just these, it's that. So it'd be 16 over 6, or 4 times 2 over 3, so it'd be 8/3. So I just have to know that this is going to be a cubic with 2 as the leading coefficient. I have to multiply that by 8, which gives me 16, and you have a 6 on the bottom, so 16 over 6, or 8/3, and that's what gives you this. And so really I can look at this and know what the ratio of the leading coefficients are going to be. So I wouldn't have to do all of this, but I wanted to show it to you, just so you could see what was going to happen. Okay? And then let me make one other point. There's kind of two cases. There's a case when you're actually starting at 0, like if I went from 0 to 3 instead of 1 to 3, it would have simplified this a lot. And the reason for that is that instead of this expression, 1 plus 2k over n, I would have just had 2k over n. This would have been 0. And so 2k over n, the function defined at that, would just be x squared of that. And so I wouldn't have had to FOIL this out. Does that make sense? So if my a was 0, it would have simplified the math a lot. And I would have just squared that and went on going. But because I'm starting at 1 here, because I'm doing that, then I have to plug in a plus k times delta x, and the a is, in this case, is 1, and so I have to FOIL. The math becomes more complicated. So the math can be simpler if you're starting at 0, and I think most of the ones in the homework, they actually do start at 0, making the math simpler. There might be 1 or 2 where they don't. Okay? And there's not a whole lot of these. There's only like 3 or maybe 4 of these on the homework. Okay? So it's not going to be too bad, and you'll feel great when you get the right answer after doing all that work. Okay? So that's the idea of these Riemann, the limit of Riemann sums here. And so you may have to watch that video twice and do a little bit of work. But I think you can get this, and when you do, I'm sure you'll feel good inside. So work hard on that, and then what I'm going to do, we'll have one more video where I'm going to give you a chance to do all of this, and then you can watch me do it, and you can see how you did. So that'll be the last video for this section.